All right, thank you. Yeah, so my name is Benjamin Trigona-Harany, and I'd like to thank Paul for reaching out and asking me to give this talk today. Um, so as you can see from the title, I'm going to be talking about how you can work with aircraft trajectories in PostGIS. So unlike the previous speaker, this is not something that I do as part of my day job or anything. In fact, this is just something I discovered recently, relatively recently, and I decided to explore it because it gave me an opportunity to learn a little bit about, say, like a corner of PostGIS that I hadn't previously used, and like what better thing is there than to use my favorite spatial database to do something interesting. So I kind of have three objectives with this talk today. I'd say the first objective is to show you where you can get this kind of like interesting data sets on aircrafts. Second, I want to show how you can get that data into PostGIS itself. And then lastly, of course, I want to look on how we can use some of the native PostGIS tools to work the data set, do some simple analysis. I think I can squeeze that all into like a 20 or 30-minute talk. And with that, I think we can get started. And in fact, I'm going to start where every flight starts, and that is at an airport. In fact, as I am speaking to you from Berlin, I took this screenshot of the Berlin airport arrivals page. And on the arrivals page, you can see that it has some, simple data about the different flights that are coming in. If we look at, say, the top one, we have an arrival time, we have the city that it's coming from to Berlin, we have the flight number. And I'll start this talk by just asking a really simple question to a bunch of PostGIS experts, and that is, well, how could we model this and the other flights inside a PostGIS database? So I'm going to start off with a very simple proposal, a very simple data model for this, and that would be this right here. So imagine we create a table where we've got a call sign. I think on the previous page, it was like TK 1707 or something. We have the departure airport, we have the arrival airport, so Berlin in this case, the time that the flight departed, and then the time that the flight left. And then, of course, because this is a spatial data set, we've got a geometry which represents the path that the plane actually took to get between those two airports. And if we just imagine what it looks like to put the data into the data set, here exactly what it is. We've got, as I said, the call sign, so the flight number, the two airports in question, the timestamps, and then a line string with those vertices from the starting airport to the destination airport. And I think that's a pretty good start. And again, we can do all the regular PostGIS stuff with this. We can find the start and end points of that flight. We can do a distance calculation, or we can do something a little bit fancier, which is, get the list of all the countries that the flight overflew as it traveled between those two cities. However, I would then ask you, is a two-dimensional line string really the best way of representing a flight? And of course, it might be good for certain aircraft who are perhaps not flying in the air, but that's not what we want to do here. We obviously want to do something a little bit more interesting. And that brings us to improvement over that data model that we can obviously have. And that would be, instead of using line string, we can use line string Z and represent that path as 3D vertices. So when we insert the data into the table, not much changes. In fact, everything is the same, except we now have that third data point, that altitude for each one of the vertices in our line string. Okay. So that's pretty good. And this unlocks a few new things with this second way of modeling our data. So we can now do a query on, for example, how high that flight was at its maximum altitude. Or we can do a 3D distance calculation using using PostGIS's tools. And so as an example here, like how close did this plane ever get to a certain location measured in 3 dimensions? And once again, I would ask you, can we do a little bit better than this when we're talking about flights? And the answer, of course, is yes, we can. So although that table had a start time and it had an end time encoded for each one of the flights, the speed at which the plane is traveling is not constant between the start and the destination, which means that the time at which it passes through each of the vertices is not necessarily predictable. So how can we make a little bit better our data model? Well, we can do that by using, of course, the fourth dimension in each one of the vertices. And that would mean encoding the data now as a line string ZM. So these four-dimensional vertices now have a time component to each of the points along that line string. And once again, when we insert the data into the database, not much changes. Everything's exactly the same, except as you can see here, we now have a timestamp. In my case, the timestamp is encoded as Unix time, but basically any kind of numeric value would work here. I think Unix time is a good option in this case. And now we have, like, I think, a very good way of representing how this plane has been traveling between the 2 points. And it goes without saying that the M value could be used for something else, all right? We could be using it to encode the speed at which the plane was traveling at that particular point in time, or something else about its state. But here we really want to focus on that temporal aspect of the plane moving through space. So these are trajectories. Okay, as I named this talk, we're talking about trajectories in PostGIS, and now we actually have trajectories once we make this small addition to that initial data model. So what is the definition of a trajectory? Well, PostGIS has a function which is called st_is_valid_trajectory. So I just literally went to the documentation, the PostGIS documentation, and I took the definition from there, and it says a valid trajectory is represented as a line string, which we have. A line string with measures and values, which we now have as well. And then crucially, the measure values must increase from each vertex to the next. And I think if we think about that, that's quite logical. You know, if that M value is representing time, time is moving forward. So the M values from each subsequent vertex must be increasing increasing as we travel down the line string. So great, now we have trajectories. And we've set up our, we've set up our database, we've set up our tables, and the natural question at this point is like, okay, how do we get some data into this database? So I'm going to take a bit of a shift away from PostGIS and Postgres for a moment, just to talk about this aspect of it. And this is going to take us into the world of something called ADS-B. So all aircraft, or let's say all fairly large aircraft, all commercial aircraft that are traveling around, are continuously broadcasting information about their current state using a variety of different protocols. The one protocol that we're going to talk about here is, as I said, ADS-B, so Automatic Dependent Surveillance Broadcast Protocol. And so you just have to imagine that your plane is continuously sending out packets of data for anybody to receive. So when I say anybody, these packets are not encrypted. They're just available over the open airwaves. And in fact, it only takes a relatively cheap receiver that you could just plug into your laptop, and you can pick up these broadcasts coming from airplanes flying above you or around you. And what is inside these packets? Well, if you get them and you decode them, you get information such as the call sign. So in the example I gave at the very beginning, we have that TK1727. You have information on the speed of the aircraft. You have information on the longitude, latitude, altitude, and of course a timestamp at which that packet was generated. Now, obviously I've underlined and bolded out those last four elements there because longitude, latitude, altitude, and timestamp are exactly the X, Y, Z, and M that I showed you in that data model. So we have actually like data coming from airplanes live all the time that exactly matches this table that we just set up. There's just one thing I want to add before I get into the actual data itself. There's another element that comes in these packets, which will just come up later in the talk, so we need to dive into it, and that is every single airframe. So like every single unique aircraft has its own identifier. And this is a 6-digit hexadecimal number, and it's example 3C6444. And these are known as ICAO 24-bit addresses or IKO 24 addresses. And these are transmitted with those ADS-B packets. So every packet has, again, an IKO 24 number. It's got those four elements that we needed for each one of the vertices in the line string that we set up. Okay, great. So what happens if you don't have one of those ADS-B receivers, right? Like I said that they're cheap and they're readily available and you can pick up live airplane data. Well, not everyone has one of these. In fact, I don't even have one of these. However, the cool thing is that there is a network of people who have these kind of receivers who are continuously sending the data that they are getting live from aircraft to this central network called OpenSky Network. And OpenSky is aggregating all of that data. And then anybody can sign up for an account on OpenSky, and they make that data available through a RESTful API. So I encourage like anybody who's interested in this, you literally go to their website and in 5 minutes you can have an account and you can start accessing this data set. Again, live data, historical data. I encourage you also to read their terms of service because it's meant for researchers, not for just any particular use case. So we're going to talk about some of these OpenSky endpoints. The first one we'll talk about is what they call their states endpoint. And this is basically where you get the live data about aircraft that are traveling, or let's say aircraft that OpenSky is aware of, right? They have coverage in many regions because there are people there who are connected and who are donating the data to the network. There's some places where there's nobody actually receiving the data, so it might be kind of dead zones. In any case, the states endpoint gives you access to all of the live information that any of their members are currently aware of. And it's a very simple endpoint. You can access it unauthenticated, and you can access it without any parameters. And if you do so, you'll get back a fairly large JSON blob. And that JSON blob will have a list of aircraft and their current states, effectively their current or their most recent ADS-B packet that somebody has received. You can also add some parameters. So the one parameter that at the top there is the ICAO24 address, which we talked about. So this is how you get information on one single aircraft. Okay, without this, you get it's actually limited to 1,000 aircraft. But as soon as you put this parameter in, you get information about one specific aircraft. And as you can see, you also can put in a bounding box. So it's expressed as latitude and longitude, minimum and maximums. And when you put those in, you get obviously all of the aircraft that are currently active in just this particular region. So let's look at one of the responses. It's, as I said, it's fairly straightforward. It's a JSON response. It has a timestamp, and then it has a list of these states. So the states, as I said before, are the most recent ADS-B packet, effectively. And here's one of them. They're called a state vector. They're, you can understand a lot of this just by looking at it. So the first element is the ICAO24 address, obviously. Next, you have the current call sign that aircraft is using. You have the country it's registered in. You have some timestamps. And then you have longitude, latitude, altitude, and then several other parameters, which we won't really get into today. Okay, so cool. Fairly easy to get the data. But now let's connect this with PostGIS. And in fact, what we're going to do is I'm going to show how you can get real-time data in a PostGIS database. And this is using a little trick called a foreign table. So PostGIS has this functionality of creating tables which don't actually contain any data themselves, but instead, when you query them, they go to some external data source. They get information, and then they present it to you as the database user as though it was coming from an actual database table. So here I'm creating a foreign table I just called it live aircraft. And you can see that the columns in the table are exactly the stuff that we said would be in the ADS-B packets. The ICAO24 address, the call sign, the time, the geometry, which is a point made up of the longitude, latitude, and altitude, and then a few other elements in it. The only difference from a normal table here is the fact that we use that keyword foreign at the beginning, and then we have to specify the server. So this is where the data is actually coming from. And of course, as you know, the data is going to be coming from the OpenSky API states endpoint, which I just talked about. Now, that's not all. You do have to define what that server actually is. And in my case, what I did is I created the server, and I used a project called Multicorn, which lets you write one of these foreign data wrappers using some Python code. So just imagine that there's some very simple Python code, which is when we make a query to this database is going to the OpenSky endpoint. It's getting that information out and it's exposing it out to the table using, just like I said, some simple Python. So what can we do? Well, oh yeah, and by the way, there's the GitHub repository that has that actual code in it. So how can we do this? Well, we can just query this like any other table. So if we say, give me the call sign, the origin country, so the country where this plane is registered, and the geometry of an aircraft called AB1644 from the live data set, we can tell that this United Airlines flight is actually at this specific point right now. And the cool thing is that this code that I wrote is actually kind of smart. When we put that where clause in there that says, give me only the information about this one particular aircraft, it actually creates the API call with the right parameters in it. So it's not calling without that ICAO24 parameter, it's calling it with the right argument to it. And that means that you're getting less data pulled from the external source, and it can be exposed quicker to the database user. We can also do a geometric query. So if we say, tell me all of the aircraft who are operating in this current bounding box, you get back a list of aircraft, again, live aircraft that are currently flying in this particular region. And yes, once again, the query is smart. It is going in and it's actually setting the longitude and latitude min-max correctly in the query when it goes to that external data source, and only getting those aircraft within that bounding box. So that's great. This is like super cool. We can access live data inside our database. Now, this is the time where I would be doing a demo, and I have this really cool demo where we can go into QGIS and we can actually show you live aircraft flying around with all their correct headings and everything. Unfortunately, before this talk, I went to the OpenSky webpage and I noticed that their API was down. So the demo is not currently possible, unfortunately. Maybe Paul, we can like splice in the demo into the videos when you upload them to YouTube with this data, or sort of when the API is actually working. But unfortunately, I'm not going to be able to do it today. Now, a lot of you are probably asking me, asking yourselves right now, however cool it is to have live data in PostGIS, I promised to talk about trajectories, and these are emphatically not trajectories. These are single points in time, and that is true. But we are now going to return to those initial database tables that I started this talk with, the 3 proposals, and we're going to show you how to populate those with actual trajectories. However, this will require 2 more endpoints from OpenSky, both of them fairly straightforward, and I'll talk through them pretty quickly and show you how you can get that data from those endpoints into your PostGIS database relatively easily. So the next endpoint is what we call like the flights aircraft endpoint. And this basically gives you all of the flights that a particular aircraft has taken between 2 points in time. So there's 3 required parameters. You need the ICAO24 address, you need a starting time and an end time. And once you provide those, you'll get back another JSON, which is a list of all of the flights that airplane has taken. And again, this is what it looks like. It's fairly easy to understand. It has the departure airport, the arrival airport, when it departed, when it arrived, and a few other pieces of information. So my suggestion is that we start to build a database that has flights in it. And you'll remember the data model. I'm going to augment it just a little bit from what I showed you in its 3rd version, and that is just to add the ICAO24 address in here. But otherwise, it's exactly what I showed you previously at the start of the talk. So let's populate it. And once again, we're going to use Python to do it. In fact, I wrote a PL Python function, and it's called OpenSky get aircraft flights, and it takes 3 parameters, the exact same 3 parameters that are required by this API endpoint. And it returns a table that looks exactly like that flights table. So exactly like this table right here. Now, in the interest of space, I could not fit the actual Python code, which makes a call to that API endpoint. It's very simple. It just constructs the URL and makes a call to it. And then you can see the rest of the code here. Assuming we get a good response from that API, a 200 code response, we just decode the JSON and we return the information as a set of rows to our table. So how do we use it? Well, we can populate our table by just inserting the responses from the API call using those same three parameters. And there we go. So in this example here, I'm asking, tell me about all the flights that happened at the beginning of June for a particular aircraft CO5F01. And as soon as we call that, and then we look at the table, you can see that there are, as an example, 9 instances of that plane that was flying that were captured by OpenSky. Of course, the problem here is that there's no geometry. And if you remember what the JSON response was, it certainly did not have any geographic information associated with it. But we can get that information because OpenSky also has another endpoint, which is called tracks. And that just says, tell me the tracks of a particular flight. So you need an ICAO24 address as usual. Then you need a timestamp, and it will return all of the vertices effectively that plane traveled through for the flight that happened at this particular time. So an API call is extremely simple, and the response is also fairly simple. Again, it's a JSON response, and it just has some simple information here. And then crucially, as you can read, it has the path, which is a list of, let's say, simplified state vectors. And again, this is more or less human readable. You can see it has the timestamp, which we can call the M value. And then it has, longitude, latitude, and some altitude, and then a few other, or a couple more data points, which we're going to ignore. So as I said, timestamp, latitude, longitude, altitude are all encoded right there. So once again, we can write a very simple Python function, which will go in and take the exact same 2 parameters. And the output of this will not be a table. It will actually just be a single geometry, a line string ZM. Once again, I didn't have space to put all of the code here, but the missing code is extremely simple. It's just constructing that API call. And then the real power is just done by the last 3 lines there, which just says, transform this into a PostGIS geometry, or more specifically, a line string, and return it to the caller. So, and yes, there's a little bit of code required here, which you can get from my repository as well, that helps construct those line strings. So that flights table, which had a number of flights in it without geometries, can be easily updated by calling this function. And we just say, if the geometry is null, well, set the geometry based on the responses from the OpenSky getTracks endpoint. And if you call that, now suddenly we have a number of valid trajectories inside our database populated for us to do whatever kind of analysis we want on at this point. So this gets us to the last part of the talk, which is to be looking at doing some spatial relationships, or how we can analyze some spatial relationships with this kind of data set. Imagine that I pre-populated a database with a number of flights coming in and out of a certain location, and that's the data set that we'll be doing some analysis on. And of course, the analysis that we're gonna start with here is like an intersection. So just like I started this talk talking about like a simplified version of our flights table, we're also going to start with like a simplified version of intersection, and that is a 2-dimensional intersection. So just asking ourselves, when do 2 lines intersect with one another? So the paths of 2 planes, when they intersected with one another in 2 dimensions, very easy to do. I'm sure everyone's done this if you've used PostGIS. Also not very interesting, because planes, as we already talked about, do not just travel in 2 dimensions. Okay, so there is a 3-dimensional intersection function that exists in PostGIS. 3D intersects, takes 2 geometries, and finds if at any point in time they intersected in 3 dimensions. And in this particular data set, I found that there were 2 flights which so happened to intersect in 3 dimensions. However, we are, of course, interested in 4-dimensional intersections. And just before I talk about 4-dimensional intersections, I'm going to introduce one final concept in this talk, and it's a concept called the closest point of approach. And this is something that you can find in PostGIS itself. And I think closest point of approach is almost like a bit of a misnomer, because it's not actually a spatial point. It's the point in time at which 2 trajectories were closest to one another. So if you look at the yellow path, the yellow plane and a blue plane, and I say, hey, when were these 2 planes closest to one another? Well, you can't just look at the spatial part of this and say they were closest at such and such point of time. You actually have to know when they were traveling, and only using that you can say, oh, it was at this point in time that they were closest to one another, and that is in fact the closest point of approach. So there's a function in PostGIS called st closest point of approach, and it takes two of these four-dimensional line strings, and it gives you the exact time at which they were closest to one another. So in this data set that I had in my database, when I ran and said, can you find the closest point of approach for a particular aircraft with all the other airplanes, it gives you back a set of times at which they were closest to one another. So this brings us to the final thing, which is four-dimensional intersections. How can we find out if two paths crossed in 4 dimensions? Well, you have to use something called ST distance CPA, which says what was the distance between 2 points when they were at their closest point of approach. So that's the function name. There's also an operator that you can see here. And in this particular instance, I was just checking for a closest point of a distance of 0 between two airplanes, with 0 meaning an intersection. And as you can see, there were no results when I ran the query on this data set. If you're thinking about it, that's a good thing, because a distance of 0 between two trajectories actually is called basically a mid-air collision in layman's terms, and we don't want to see that in our data set. So fortunately, we did not find that here. However, I did run it again, and I just looked for, well, were there any instances where the closest point of approach was pretty close to one another? So I chose an arbitrary value of, was there any time when two planes got within 1,000 meters of one another? And in this data set that I had, I found that there was 2 instances. So in one instance, they were 142 meters apart, so quite close. And in the second instance, they were 780 meters apart from one another. And I also calculated that out as horizontal separation and a vertical separation. And just as I wrap up here, I'll show you exactly what those 2 cases were. So the second case where they came within 780 meters, it was one plane flying north and one plane flying south. And in fact, this is kind of a normal thing, because planes follow sort of defined corridors, and the vertical separation of about 1,000 feet is pretty normal for airplanes. But then you're probably asking yourself, what about the other case where they had a vertical separation of 0, and they were quite close in the horizontal? Well, it just turns out it was 2 planes on the apron at Zurich Airport, so nothing really to be too worried about. And that's all I think I have time for today. So just as a wrap up, here's the links for everything that I showed you. OpenSky, a couple of GitHub repositories, which have there's a Docker container with all of the code and everything that I showed you in it, and a couple of supporting libraries that I also have available. And yeah, I hope you enjoyed it. Like I said at the beginning, this is not something that I'm necessarily an expert in. This is just something that I discovered as I was learning about the capabilities that PostGIS has for this kind of data set. And I thought it was interesting, and I'm happy to share it with the group here.
Awesome. Thank you so much, Ben. I was wondering, you've got a lot of mileage here. You've got a data set I'd never heard of in OpenSky. You've got live access to it by FDW. Got a really technical question to you about the FDW, but I won't inflict it on everybody here. What do you take away from this in terms of like the big, what's the thing that sort of made you surprised about what you could do?
Yeah, well, look, I think I knew from you actually, Paul, that PostGIS had this support for M values. But my big takeaway, again, this is like my personal learning, was that there's actually functionality already built into PostGIS natively to work with this kind of data. And that just wasn't something I was aware of. I didn't know it had trajectory support. And I know that there's a talk later today, which is going to show a further extension to PostGIS, which provides, I think, even more capabilities around trajectories. But I would say, like, for doing a lot of things right now, PostGIS never ceases to amaze in terms of like the things that you can find that it can do natively. And for me, that was maybe the most interesting part of this experience for me.
Awesome. Well, thank you very much for this talk. Everyone is blown away by all the bits you brought together into one little talk.
Yeah, I appreciate it. Thank you.